Okay, next up we have lesson 2, which is properties of exponential functions. So in this lesson, we're going to go into a lot more detail regarding exponential functions and their graphs, and a little bit about their table of values as well. So if we look at our learning goal here, you're able to identify the properties of an exponential function and then explain and prove why some of those properties exist. And on my site here, you'll see that in the background section, I mentioned that exponential functions are really useful in the real world. They're often used to model different things that occur, different phenomena that occur in the real world. For example, they're used to model and predict populations, carbon date artifacts. They help coroners determine time of death, compute investments, as well as many other applications too. Okay, so understanding the properties that make up an exponential function, as you'll learn in this lesson, is very important in helping you understand how to solve real-world applications later on in this unit. All right, so we've got to go over these properties and gain a deeper knowledge of exponential functions, because you'll see later on in the unit we'll answer more of the real-world applications of it. And obviously having the fundamental knowledge of the functions and their properties is only going to help us understand why we get to the answers we do later on in the unit. I had you all do an investigation, so you do have some background knowledge when it comes to exponential functions. So that investigation was done on Desmos. And without further ado, let's begin our lesson here. All right, so an exponential function is a function that has a variable as its exponent. Usually the letter x is what is represented there, but I mean, it could be any letter. It's just a letter, but usually in math, we tend to use the letter x. So in the exponent, there's a variable. We haven't seen that before. All right, we have not seen that before. In the actual exponent itself, there's a variable. The general form of an exponential function is in the form of y equals b at x, or b to the power of x, where b must be greater than 0 and b cannot equal 1. Okay, b cannot equal 1. Why can it not equal 1? Well, because 1 to the power of anything is still just 1. All right, so it doesn't actually create an exponential curve, because all our answers will always be 1, like 1 to the power of 2, 1 to the power of 3, 1 to the power of 10, 1 to the power of a million is always going to just be 1. Some definitions and some recap. Domain, remember, because we're going to be doing domain and range again in this lesson as we learn about some of these properties in exponential functions. So the domain, the set of all values on the independent axis. Okay, so all the values on the independent axis, which is usually our x-axis. Again, you could use any letter, but in math, we most of the time use x. That can go into a function. So so all of the values of x that can go into a particular function is the definition of domain. For range, it's the set of all values on the dependent axis, usually the letter y, that can result from all the inputs. So all the values of x that you can put into the equation, okay, or into the function, the result of which will give you your range. So when you basically, let's say you have y equals 10 to the power of x, okay, your range will be dependent on all the x values that you plug in, right? And all the possible x values that you can plug in. That will give you all the possible y values that can occur. All right, so for this, I'm going to ask you, in class, I'll be asking you to go into Desmos, but I've already done it. Okay, so I've already set up Desmos, and let's take a look at the question itself. Okay, so by the way, when you're in Desmos, make sure that you do the following. So notice I put here in the wrench located in the upper right corner, change the settings to the following. So for the x, so let's take a look what that looks like. Let's go into Desmos. Here's the wrench in the top right corner. And you can see that you can change the x values and the y values accordingly. Okay, so basically it's what is showing on your screen. So you can choose the range of x's and the range of y's that can be viewable on your screen. So change them accordingly to these numbers here. -5 to 5 for x and -2 to 10 for y. All right, so let's dive right in and let's graph a few exponential functions and let's see what properties we can distinguish between them. All right, so use your graphing calculator to plot these three equations. So if I go into Desmos, I'll show you quickly how that's done. Okay, so let me just put in my values here. Okay, so once you have your values, okay, you can type out equations. And the way you type out equations, so if I were to type out y equals 2 to the power of x, I simply would hover into this screen here, or this portion of the screen there where it's blank, and then just type in y equals 2. Now to do exponent, press this button here, which is your power, so 2 to the power of x. Okay, and there you have your graph. So go ahead and graph all three of those curves on Desmos. All right, so learning how to use that graphing calculator can come really in handy. And you'll see we're going to be using it throughout our homework where you're going to be asked to go into Desmos and graph different equations. So it's best to get the hang of it now. And you would sketch and label those curves as you see them here so that they're in your notes. But I have just taken a screenshot of what we had we can analyze my screenshot here. Okay, but for your notes, I would probably just draw the curves yourselves, just using some critical points. Pick a few critical points and try to draw the curves. So you can see that my blue line, this is y equals 2 to the x. This is y equals 4 to the x. And then this is what y equals 10 to the x. All right, so let's try to decipher some differences between these three curves. All right, so remember that our equation is in the form of y equals b to the x. Well, these are in that form, okay, where b is just these base values here, 10, 4, and 2. Okay, so let's take a look now and answer some questions. All right, so what do these graphs have in common? So let's take a look at these graphs. What do they have in common? Well, I would say that they all have a y-intercept at 0, 1. Okay, so let's write all have a y-intercept at 0, 1. So they cross through the y-axis at 1. What else is similar about these? I would say that they are also all going in the same direction. So they're rising from left to right. Okay, so rising from left to right. Okay, but that can actually, now that I'm thinking about it, we can actually just put that point down in here where it says, how are the graphs similar? Because although they have that, they are going, they're rising from left to right. I mean, they're not identical curves. So why don't we, instead of putting that there, let's save that for our next portion here. Let's write it here, okay? So rising from left to right. Okay, so there's something else that's in common that's the exact same for these two, for all three of these graphs, which I haven't discussed with you yet. And that's an idea in math called an asymptote. All right. Now, up here, I did not discuss this definition with you yet, but right here is a definition of an asymptote. It is a line that continually approaches a given curve but does not meet it at any finite distance. So you're probably looking at that and thinking you have no clue what that means. And I think the best way to explain it is to actually look at the graph itself and make sense of it that way. So if I were to tell you that all three of these lines or curves have what's called an asymptote, a horizontal line at y equals 0. So passing through the y-axis at 0, there's this horizontal line. And so if I were to mention that to you, maybe you can start to make sense of what's happening here, okay? And if I switch to Desmos, you'll be able to see even better. You'll see that as I zoom in, into this curve and I keep going to the left, you can see that it keeps getting closer and closer to the line of y equals 0, okay? But it's never actually touching it. You can see as I keep zooming in, it actually never touches the line of y equals 0. It keeps getting closer and closer to it, but it never actually happens. It never actually touches. So why is that? Why would that happen? Why do these three curves never cross this line here? It actually never touches or crosses this horizontal line here. So let's analyze quickly why that happens. Well, let's say that we're dealing with x values that are really far in the left direction. So these are our x values, right? And that's our y. Let's say we're inputting an x value that's really far in the left direction, okay? So let's say negative 100 as our x value. If we were to plug in for y equals 2 to the x, if we were to substitute x equals 100, what would we get for y? What would our output be? Okay, so let's see, y equals 2 to the power of 100. Okay, pull out your calculators, and what do you get when you type in 2 to the power of 100? Okay, so pull out your calculators now and try that. Sorry, my bad, negative 100, because we're far to the left, right? So make sure you do 2 to the power of negative 100. Okay, so type that into your calculator. You get an ever so tiny decimal, right? Tiny, 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 tiny decimal, to the point where you probably can't even fully comprehend how small the decimal is, okay? And if we continue to keep going and we say, okay, what about y equals 2 to the power of negative 1,000? The decimal actually gets even smaller, but it never actually gets to 0. You can keep trying it. You can do 2 to the power of negative 10,000 and 100,000. The decimal will continue to get smaller and smaller and smaller to the point where you would get like 0.00000000000, maybe 30 of those zeros, and then 1. So it actually will never end up reaching the point of 0. Okay, because there is no way of getting 2 to the power of anything. You will not get a negative number. Okay, you will not get a negative number, nor can you get a 0. I mean, you can choose any numbers to plug in there. You will never get a negative number or a 0 there when you're substituting values in for x. All right, so it keeps approaching this invisible, what's called asymptote, or a horizontal line, but it never touches it. So what do they have in common? All have an asymptote at y equals 0. Okay? All right. What else do they have in common? Is there anything else? I mean, I guess we can say, um, that they are all increasing, right? The further we go to the right, the more that they're increasing. So the larger the x value we input, the more they are increasing, right? They keep going higher and higher and higher. These curves keep moving up and up and up as we keep inputting larger x values into our equation. For example, 2 to the power of 10, okay, versus 2 to the power of 1,000. Obviously, 2 to the power of 1,000 would be a much larger y value than 2 to the power of 10. So this keeps increasing as we input larger x values. So increasing, let's just write increasing rates. Okay, so how are the graphs similar? I think we made note of it. They are rising from left to right, and they are increasing rates, okay? But they're not exactly increasing at the same rate, right? So they're not exactly identical to each other clearly. We can look here and see that y equals 2 to the power of x, okay, seems to grow at a slower rate than y equals 4 to the x. And y equals 4 to the x seems to grow at an even slower rate than y equals 10 to the x. So hopefully you see a pattern here that the larger this value is, 2, 4, 10, and if we keep going, the steeper or the faster the increase is going to take place. Okay? So let's make a note now of what we just talked about. So the larger the value of b, this is just to make a little note here. The faster the increase occurs. Right? So that means the graphs are different in that they don't have the same increasing rate. Okay? So curves do not have an identical increasing rate. Okay, they're increasing, I mean, they are increasing, but they're not increasing at the same rate. The domain and range, let's take a look at what our domain would be. What values of x do you think are possible for these exponential functions? What values of x? Well, any value of x is possible to substitute in here, right? This curve goes on forever in this direction and forever in that direction, which means that we can substitute any values of x all the way up to x is a billion potentially, and all the way down to x being negative a billion. We can substitute any values of x because this curve keeps going on forever in the left and right direction. All right, so the domain is simply x is an element of any real number. Okay, so any number, and that could be decimals, it could be negatives, positives, it could be totally, absolutely any value we can substitute in for x. Okay, the range, however, okay, remember we do have to write that y is an element of real numbers, except for the range, there's a restriction. There was no restriction on the x. It could go on forever in both directions for x. But for y, there is a restriction. What do the y values always have to be? Greater than 0. It will never touch 0, so it's not greater than or equal to. It always has to be greater than 0. So in the second part of our range, just write y must be greater than 0. So y could be any real number, which means that you can get decimals and that are above 0, but you can get any sort of decimal values, whole numbers, it doesn't matter. The only restriction is that the y's have to be above 0. Okay? Describe the impact of changing the base on the graph of an exponential function. And that's kind of where this note comes in, where we said the larger the value of b, the faster the increase occurs, or the steeper the curve. All right, so we can just kind of put an arrow there. Okay, so that covers all those questions above, covers when b is greater than 1. Okay, so all these questions above are for b greater than 1. So that means it could be 1.1 all the way up to whatever. Okay, what about when we get b values that are between 0 and 1? Because that's possible as well. All right, so what happens when we get b values that are between 0 and 1? For example, y equals 1/2 to the power of x, 1/4, 1/10. And remember that this just means y equals 0.5 to the power of x, y equals 0.25 to the power of x, and y equals 0.1 to the power of x, right? So again, you would be sketching this in Desmos, these three curves. And I don't care if you plot the fraction version or the decimal version, you can plot either one. I've already plotted them, and take a look at what I got. It's actually going in the opposite direction of the questions we did above, right? The questions we did above went this way, okay? These ones, or these curves between 0 and 1, seems to be only going down and to the right, okay? Down and to the right. So let's take a look at which graph is which. So our purple curve here is y equals 1/2 to the x. All right, the black curve is y equals 1/4 to the power of x, and then the red curve is y equals 1/10 to the power of x. So let's look at this and analyze it. They all seem to, again, have the same y-intercept. And by the way, I didn't go over this last time, and I really should, is why do they have the same y-intercept? Well, let's think about what the y-intercept means. The y-intercept occurs when x is 0, right? That's when the y-intercept occurs, when x is 0. So you're substituting 0 for x to find the y-intercept, right? So if I wanted to find the y-intercept of y equals 2 to the x, I would sub 0 in for x because that's when it occurs. So 2 to the power of 0, and guess what? What is any number to the power of 0? 1. It doesn't matter if it's 10 to the x. When you substitute a 0 for x, you still always get 1. And so that's why they all share that common y-intercept. And the same applies down here. All right, it doesn't matter if it's a fraction. Anything to the power of 0 will equal 1. Any values to the power of 0. All right, so they all have a 0, 1 point, which is your y-intercept, where x is 0, y is 1. All right. Also, we're seeing that the 1/2 x, which is 0.5, right, 0.5 to the power of x, seems to be less steep than the others. Okay, it's less steep. Whereas y equals 0.25 to the power of x seems to be getting more steep, and y equals 1/10 to the power of x, or y equals 0.1 to the power of x, seems to be the steepest of the three. So maybe we can draw a conclusion that the closer we get to 0, okay, so when b is between 0 and 1, right? The closer you get to 0 for b, so the closer b is to 0, the steeper the curve. All right, so that feels somewhat confusing, right? But the closer you are to 0, only when b is from 0 to 1, the closer you are to 0, the steeper the curve. All right, so I'd say that we've analyzed these three graphs. Let's now get our information down on paper. What do the graphs have in common? Okay, so what do they have the same? They have the same y-intercept at 0, 1. They all also, again, have an asymptote. They will all approach, if I go back up, again, they will all approach this line of y equals 0, but never touch it. It'll keep getting closer and closer and closer and closer, all the way to infinity, but it'll never touch 0. It can't be. You cannot get 0 when you do 1/2 to the power of anything. Okay? So you cannot get 0. So asymptote, again, at y equals 0. Okay, and then I guess the other thing that they have that are similar, right, is that they are all decreasing rates from left to right. Okay, so they're all decreasing rates from left to right. How are the graphs different? How are the graphs different? Well, they have different decreasing rates. So different, right? Some are more steep than the others. Different decreasing rates. By the way, you're probably wondering, why is it decreasing? And let's analyze a table of values for a second. Okay, I'll show you why it's decreasing. Okay, so suppose we plug in or substitute the following x values, because we can substitute any x values. You can see it goes on forever in both directions, this curve. So let's go with -2, 0, and then +2. All right, and let's do it for the function y equals 2 to the power of x. So let's substitute these x values in for x and see, why is it decreasing? Okay, so why is it decreasing? So let's see. So we have, in the first one, we have 2 to the power of -2. If you punch that into your calculator, you'll see that you get 0.25. You can also use your exponent laws and do 1 over 2 squared, which is 1 over 4, which is also 0.25. But I mean, to go quick here, you'll punch that into your calculator and see that it is 0.25. What about 2 to the power of 0? Well, we know that equals 1. That's our y-intercept. And then what about 2 to the power of 2? Oh, I just realized I am using the incorrect base. I apologize for that. Let's just fix that really quick. It should be 1/2 to the power of x. Okay, I apologize for that. So let's do 1/2 to the power of -2. Okay, so 1/2 to the power of -2, if you were to punch that into your calculator, actually equals 4. Okay, so 1/2 to the power of -2. Then 1/2 to the power of 0 is 1. And 1/2 to the power of 2 is actually 0.25. So you can see that as my x values are getting larger, my y values are doing what? They're getting smaller. And they're going to keep getting smaller as I keep inputting larger x values. And so that's why we have a decreasing function here, okay, which is important to note. Let's state the domain and range. Well, the domain is still x is an element of all real numbers with no restrictions, right? Because this curve will go on forever to the left, and this curve will go on forever to the right. So we can use any x values, decimals, all the way up to -1 trillion to +1 trillion. It doesn't matter. We can use any x values. These curves are going to keep going on forever, theoretically. The range does have a restriction, and it's actually the exact same as all our previous sets of questions. It's still YER. Y is an element of real numbers. They can be decimals or whole numbers. And it's still that all the y values have to be greater than 0. It'll never touch 0, but they all have to be greater than 0. Okay, so now we're going to describe the impact of changing the base on the graph of an exponential function. Okay, describe the impact. So when b is between 0 and 1, okay, the closer the b value is to 0, the steeper the curve. Okay, so these are all just properties, all right? So the closer that you get to 0 as a decimal, like for example, 0.1 is closer to 0 than 0.5. The closer you get to 0, the steeper the curve. Okay. All right, so maybe we should take a minute now and just summarize everything that we've looked at here. So for y equals b to the x, where b has to be greater than 0 and cannot equal 1, we have found that y-intercepts, and this is strictly for y equals b to the x, okay? There's no variations of this from last year. There's no horizontal stretches or compressions or shifts up or down, okay, or left or right. This is strictly for just y equals b to the x. The y-intercepts are 0, 1, okay? Asymptotes at y equals 0. When b is greater than 1, it is an increasing rate. So like the first sets of questions, it's going up and to the right. When b is between 0 and 1, okay, but not equal to 0 and 1, but between 0 and 1, we have a decreasing rate. Okay, and then we can make note of the fact, and maybe I should have put it right under there, but the larger for this particular point here, okay, so for this right here, the larger the value of b, the steeper the rate, or the larger the rate. For this one, when we have b is between 0 and 1, okay, the closer the value of b is to 0, the steeper the rate, or the larger the rate, the steeper the curve. Okay, I'd say that's a pretty good summary for strictly y equals b to the x. They have y-intercepts at 0, 1, asymptotes at y equals 0. When b is greater than 1, we have an increasing rate, and the larger the value of b, the steeper the curve. When b is between 0 and 1, it's a decreasing rate, and the closer the value of b is to 0, the steeper the curve is there. All right, so I'd say that's a pretty good summary of some of the main characteristics of exponential functions. There's going to be another part to this lesson, so please watch the next video as part of this lesson.